Thank you, Cormac. As Cormac mentioned, my name is Marco Esters. I'm a postdoc in the Cortorola group and at the Center for Autonomous Materials Design. And I will demonstrate how to work with our data, how to search for our data using two different tools. One is a graphical user interface, which is our search page, and the other one is an API that you can use to access all this programmatically. And I will start with the search page. Most of what I'm doing right now is what I'm doing for the seminar is going to be done in the browser in your Colab notebook, but you also have a PDF available for the API part in particular in case you get lost or can't follow along. All the commands that I'll be using for the search API will be available in the PDF. And in the end, I will also provide a fully filled out Colab notebook so you can compare or check the parts that you maybe didn't quite, weren't quite able to follow along. So without further ado, let's open our browsers. As Cormac mentioned in the introduction, we have a website called AFLOW.org. And if you scroll further down, you see we have a large database with over 3.5 million entries that is the largest materials database in the world that's publicly available. So there's a lot for you all to search for, and we will do this first with the Mendelib search, which is our search interface. You see it's typical a periodic table, and why don't we do a simple search to get started by just looking for compounds in the ICSD database that we have containing chromium. So we just click on that chromium symbol here, and we want to limit ourselves to, let's say, 3 species. If you are interested, for example, in ternary compounds, you use that drop-down menu here on the side. Oh yeah, first of all, can everybody read everything clearly? Is it big enough? Or do I need to zoom in a little bit more? I see some thumbs up. Excellent, thank you. So if you click on the drop down menu, you can limit the number of species. You can also, when you switch to range, or say that you want between 2 and 5 species, but we are now looking for just 3. And when you click on search, start searching, you see you get a bunch of ternary compounds, mostly it looks like chromium chalcogenides here that all contain chromium and have 3 species. Here we have some aluminum silicon species. So that was a simple search. We can also look, instead of looking for elements, we can look for element groups. We have a little grouping section here. For example, let's look for halogens and chrome. So when you just click on halogens, it will add it, and it will look for anything that contains chromium and either fluorine, chlorine, bromine, or iodine. Search again, and you see we have a bunch of chromium halides. We use bromine, chromium oxide, bromine, chromium sulfide, etc. So all these, that is one thing you can do. Another thing that we have are logical operators. So let's reset the search here, and let's look for ternary chromium compounds that do not contain oxygen. And to do that, you have these like logical operator panel here. So what we want to do is we have chromium and not oxygen. Assume you're not interested in oxide, you can search. That way you see the oxides that you saw in the prior search, they're all gone. So you see, if you scroll through all of them, you will see there's not a single compound here that contains oxygen. So that's something that you can do, and you can make these logical statements to be almost pretty much arbitrarily complex, as long as they make logical sense. So just to give you a quick example, you can, for example, instead of looking for not oxygen, you can look at chromium and, let's say, selenium or tellurium, and you will get, in the end, results that will contain either selenium or tellurium, maybe both. That's logically also possible. So you can, as you can see, make these search queries for the species to be as complex as you like. If it's too limiting, of course, you may not get anything back, but it can be as complex as you want. So that's all nice, but a list of compounds that we have in the database is not necessarily useful. What we want is what they can do, what are their properties. And for that, we have a section in the search page when you click on this link here, that is the properties filter. If you prefer to have everything more on one page, if you don't like swiping, if you prefer scrolling, you can just switch that slider and everything is on one page. And if you don't have your browser open in private mode, it will actually save these settings, so you don't have to do this every time. I personally prefer the compact mode, but that's a matter of taste. So now let's, for example, look for anything that has a bulk modulus. You can either click on the mechanical properties part and search for the bulk modulus, or if you don't want to click through everything to figure out where which property is, we have a search field up here that, for example, let's look at the VRH bulk modulus, which is the default or the most reliable bulk modulus, and we can search, and we see we have about 8 entries with these particular search queries here, and we can sort our properties with these buttons here. You see the highest one is some chromium oxide, chromium tellurium oxide, and the lowest is silver chromium tellurium. And if we click on this link here on the left, we get to our so-called entry page. This entry page contains everything that we calculated for this particular entry. We have some structural visualization that you can play with. I think Dr. David Hicks will later talk a little bit about the symmetry feature that we have for some of these compounds. And you get to a lot of different pieces of information. For example, our structure, the structure parameters, prototype information, symmetry information. There's a lot of symmetry information, the reciprocal lattice. Here are some thermodynamic properties. We have some thermal conductivity calculated for this one, thermal expansion using the Devine-Greeneisen model, Debye temperatures, and here are the mechanical properties. We have a lot of those too. And we have beta charges calculated, and here at the bottom you can also see the band structure for this one. It's a magnetic compound, so you have a majority spin and a minority spin band, and the density of states that are atom projected. So there's a lot of things you can play with, and we also published our input files if you want to reproduce these calculations for yourself or just compare it with our database. Are there any questions so far about the search page? There's a question.
I have a quick one, and I might have missed that when you went through that. What's the origin of the band structure calculations you're showing?
You said the origin?
Yeah, where are they, you know, are they calculated, or are they extracted from literature?
Yeah, we calculate the band structures using density functional theory. Using density functional theory calculations.
Okay, you have the details on that somewhere probably in the instructions, so I step back.
We have for the band structure, we have where is it? We have the K points for the band structure calculation and the INCAR here. So if you're familiar with BASC, you can take these files, and we also have up here, the relaxed positions. So you can reproduce
Okay.
this easily.
Okay, excellent. Thank you. That's what I was after. Thank you.
You're welcome. Any more questions?
If you wanted to change the k-path on the band structure calculation, would that be at all possible if you wanted to explore some like non-high symmetry direction in the band structure?
With AFLOW, you can give it a custom k-path, yes. But with AFLOW, we have, this is going more into the AFLOW section. These are very good questions, but we have standard paths. There is a paper, if somebody can post that in the chat, that shows how we get to these standard paths. But if you use the actual AFLOW code, you can use your own k-path if you so choose, yes. But for these here, for this app here, these are all pre-calculated. We unfortunately, you cannot use your own path to visualize this band structure because we only have it calculated for this standard path. Thank you, Corey. The paper for our default paths are posted in the chat. And the AFLOW standard parameters, thank you very much. These are basically the papers that are the basis of our calculations.
So yeah, just to add to what Marco said, so you would have to redo the DFT calculation. However, if you do have the relaxed structure there, so instead of having to redo it all the entire relaxation, you can just start from the relaxed structure and then use this to calculate it with a different k-point path. So if that's what would be the way to address the question you had.
Yes. So then without further ado, let's go to the Colab notebook where we have some exercises for the search page. I will post the link in the chat. I also already have it open in the browser. So let's open the AFLOW School Database AFLUX IPython notebook. And the first thing we want to do, very important, is to click on File, as Professor Torres said in the last section, and we save a copy in Drive. There's a question, Eric.
When you're trying to open this AFLOW system, you brought up the file with all the script pages and you say to open with, I only have like 3 options to open with and none of them seem appropriate. What was the name of the application to take it from this screen full of code line and make it readable?
Should be open with Colab. Are you, okay, do you have a Google account?
Yeah, correct.
Gmail. Are you logged into your Gmail account and the browser?
Correct.
So you probably see this. Do you see this? Do you see this screen?
I have an open with tab, but it does not have Google Collaboratory. So I'm going to connect more apps and see if I can search for that.
Yeah, I mean, it should work if you have if you're logged into Gmail in the same browser session.
I am, yeah.
Eric, it's not allowed to be used with a virginia.edu account. I had to log into my personal Gmail in order to connect Collaboratory.
Yeah. So
Okay. I misunderstood that. Thank you so much. That's the problem.
But if you've never used it before, you'll still have to go to connect more apps and then it'll be on that page.
Yeah, Marco, you should be able to send the Colab link instead of the Drive link.
Yeah, if they,
Yeah, I think that works. If you actually,
Yeah, if you
send them
copy paste that, exactly.
yeah, try this link. Thank you.
That should work better than the Drive one because you need to connect your Colab to the Drive, so it's better to send the Colab link.
Does that link work?
Yes, that seems to have worked. Brought it straight up. Thank you guys. So sorry for the problems.
No worries. Just make
No
sure to make a
worries.
copy of it
Okay.
so you can actually work with it.
Save as copy.
File, save a copy, and Drive. Yes.
Excellent. Thank you so much.
But here we have some exercises for the search page. If you want to just enter your own solution, just double click on the field, and there are 3 exercises. One, to use the search page to find a band gap for manganese dibromide in the space group 164. And for that, it will be very useful to look at the space group symbol here. And the second one is to find the bulk moduli for materials containing titanium in the ICC catalog, to check for the one with the highest bulk modulus and what the lattice type, check what the lattice type is. And the last one is to just find the shear moduli of materials containing at least one halogen but no chalcogens, and to check which material has the highest and lowest shear modulus. And for that, I think I will give you, at least for the first two exercises, I think about 5 to 10 minutes, and we'll just reconvene after that. If you have any more questions, just feel free to raise your hand, ask them, or ask them in the chat. I will demonstrate how to do them using the search page. The first one was to find the band gap of manganese dibromide in the space group 164. So for that, let's reset the search. We first of all need to check the species. One is manganese and the other one is bromine, and it's a binary compound, so the number of species is 2, and what we want is the band gap. So when we're looking in the search page, in the properties filter, we have 2. When we type in band, we have 2 properties. We want the electronic band gap, so we add them to the search, and then we start searching, and you will see that you have 3 compounds. One of them is manganese dibromide in the space group 164. And the band gap is 3.38 electron volts. If you want to be, you can also restrict the value for the space group from 164 to 164. I didn't demonstrate it, but it's something that you can do. And you will only get this one result, manganese bromide, 3.38 electron volts. So let's add in Colab notebook. The next exercise was to find the VRH bulk moduli for materials containing titanium. So let's reset the search, start from the beginning. Bulk modulus is what we were looking for, and it needs to be any entry that contains titanium. So now what we want is the one with the highest bulk modulus. So we sort the highest number, and we see it is iridium-3 titanium. So the compound is iridium-3 titanium. The lattice type, we can go to the space group and the metal insulator. The space group is already visible here. It's 221. But for the rest, we will have to go to the entry page here by clicking on it. And the link will load everything. And we're looking for the lattice type. And the lattice type is, the Bravais lattice here is CUB, which is simple cubic. And if it is a metal or an insulator, we can just look at the band structure or the density of states, and we see we have bands crossing the Fermi level, so it is a metal. Then for the last exercise, the shear moduli for anything containing one halogen but no chalcogens. Now let's reset the search again. We want a halogen and not a chalcogen. So you can really use these element groups as if they were an element, and we want the shear moduli. So let's look for the VRH shear modulus and add them to the property filter. And we can then sort. The one with the lowest is titanium tetrabromide. The one with the highest is magnesium, it's magnesium fluoride nitrate. fluoronitride. So highest shear modulus was 0.4 Ti, and the lowest was F3 Mg3N. Any questions about the search page so far? See a raised hand. John, please.
I have a question about the accuracy of the results. So are the band gaps corrected, or are they just straight out the DFT?
They are straight up DFT. We don't use HSE or anything like that. We have some calculations. I think the SSD calculations have a Hubbard U, which I think we will is it in the standard parameters paper? I'm not 100% sure.
Yes, the in general the band gaps are corrected. So they are corrected with the plus U parameter, the Hubbard U.
But
And that is part of the standards paper, the standard parameters paper. Yeah.
Yeah, there's a table with the list of views, and also you can find, so for any given entry, you can also check that the use will be in that entry page. And you can, I think you can also search, I'm not sure if you can search by use, but you can definitely ask for it to return the U values within AFLUX.
yes, you can. You can search for use in the. We look at the calculation details. There are LDAJ, which orbitals, the type, which are either none or the DUDRF, which are using the DUDRF scheme, and the U parameter. So yes, you can search for those two. Any other questions? I don't see any raised hands, so I'll move on to the search APIs. So we all saw the search page, which is great if you just want to look something up real quick, or if you want to get a quick overview of what kind of materials we have. But the search page is really only useful if you are actually just looking at something, you know, with in a human readable format. But if you want to use this, for example, for big data analysis, or if we want to use this for machine learning, a graphical interface is not helpful. We need a way to programmatically access our data. And for that, we have a search API called AFLUX. The aim is essentially to combine the search page, or to model the search page in a way that we can use this with a programming language like Python or anything really that can query a URL. And that is the principle behind AFLUX. We're deploying a search functionality that uses the query part of a URL. And this is how AFLUX is structured. We have our server for the API, which is aflow.org/API/AFLUX. And the query, which consists of a so-called matchbook and a so-called directives. And I will go through how to build such a matchbook and how to build directives. It has a little bit of a learning curve, but the more you play with it, I think the more you will understand how AFLUX is working. I will go through the matchbook first and then talk about the directives. The matchbook is essentially any kind of keywords with arguments that you use. So anything that you would traditionally consider to be part of a search function. All the stuff that we did before with selecting elements, adding properties, that is all part of the matchbook. And the keyword list that is available is in the so-called help directive. And when you click on this link here, open it in a new tab, you see that we have a JSON. If you don't have Firefox, you may have, it may look like this, but on a Firefox, you have it more nicely formatted. You see a JSON that contains all these parameters, all the keywords that you can use to search, and all the properties that we have calculated to search in your AFLUX query. So I'm using Colab to use kind of a Python-like interface, but all of these links that will be printed can be used in your browser, or you can use, for example, wget or curl or any other programming language that you like to query these URLs. And essentially how all of this will be structured is we have the necessary packages. We will build the request together, we'll print it, and then also print the response. So if you go into the cell, for those of you not familiar with Colab or Jupyter, and hit Control Enter. So to run the cell is Control plus Enter. I'll post that in the chat as well. And you see at the beginning, fortunately, Colab always scrolls to the very end. Jupyter doesn't. You see the link that I'm using to generate the output, and below the link, you always find the output. Here you see we have the JSON, the same JSON that I just opened in the browser. So if you don't like Python, you can always just type the links manually into the browser, and you see it's all aflow.org/API/AFLUX, and then after the question mark, there's a query that you can use. The directives are formatting instructions, and we will particularly look at the paging directive later, but we also have the help directive, which displays readmes. Format can either be JSON or HTML. JSON is particularly helpful for Python or any kind of programming that for machine learning. And paging controls the number species and a little bit of sorting. We'll go through that together. AFLUX is using logical operators, just like what we did in the search page. You saw we used AND operator and NOT operator, and AFLUX can do the same. It has a few more, and we will go through them piece by piece and kind of see what they can do. We will use a few properties, mostly species, end species, and catalog, but also the band gap, just to demonstrate the features of AFLUX. Let's jump right in. This may be collapsed, so just take that little arrow, that little triangle to unfold all these commands for the operator series. So you see there's a bunch of it already filled out, and we will focus on the matchbook. We'll build the matchbook together. All the other stuff you can ignore pretty much. It's just putting the link together because it works. Using Python is just a lot better for a Colab notebook. So let's build up first AFLUX search. So we want, for example, in the ICSD catalog, search for compounds containing chromium and 3 species. That is the first search that we did in the search page itself. We're using the GUI. So we use these properties here. For example, we want compounds containing chromium. So we use species. And then in parentheses, chromium. So we are looking for anything that contains chromium. We want 3 species, and the appropriate property for that is n species. So we separate this with a comma and type n species parentheses 3. And at last, we want it in the ICSD catalog, and the appropriate keyword for that is catalog ICSD. If you are looking at it without the catalog, you're looking through the entire AFLOW database, which is 3.5 million entries. So that just makes the search go much slower. So let's just limit ourselves first to the ICSD catalog. And again, running the cell with Control Enter, you see that the request here is taken away from me by Colab, but here's the request that this piece of code here is putting together. You can also use this link and put it in a browser, and it will work just as well. I can demonstrate this by clicking on it, and here you see We have a pre-printed output and it is a JSON. It works in the browser just as well as in Colab Notebook. We see we have 862 entries, and this is you can convince yourself that this is really everything by doing the same search in the search page. In fact, the search page uses AFLUX as the engine behind the scenes. You see there are a couple of properties that are returned, that are default. The compound here, silver chromium oxide. Then we have an AUID, which is our unique custom identifier. The AURL is something that we won't be talking about today, but this is at the location where our data is, the raw data is. We have the space group and the Pearson symbol, which is what you also see in the search page as default parameters. The species here listed as an array, and end species and catalog because you were looking for them. This is a very important part to understand. So are there any questions about this? We have the, yes, Ian, please.
Yeah, so I guess I have two quick ones. First off, you said that the directives can be JSON. Is this format with the keyword and then parentheses always the format for Matchbook?
Yes.
Or can you
yes.
submit that as like, okay, cool. And then secondly, if you were looking to return a value but didn't have like a specific number that you wanted it to be, like it would be silly to return end species arbitrarily because you can just count them. But like if I just wanted it to tell me end species in one of the JSON fields, how would I do that?
I will get to that in a little bit, actually.
Okay.
But the answer is to not have that limit in here.
Okay, cool. That's basically what I was curious about.
Yes, we will get to that in a little bit because there's also a little pitfall in that, and I will elaborate on that a little bit later.
Okay, excellent. Thank you.
Okay, I don't see any raised hands, so let's build some more search queries just to get warmed up. So now we do the second search that we did, and that is exclude oxygen from the results. So we have species, chromium, and now we're using the and operator, which is a comma, the not operator, which is the exclamation point, and then oxygen. So this one means chromium and not oxygen. Again, end species is 3, catalog is ICSD. So I can actually, let me put the matchbook in the chat for this one. So we can do the same logic that we can do in the search page, except for now we get a JSON back. And here's the link that you can use in your browser or whatever programming languages you prefer. So that was the not operator. Now the or operator. We can, of course, we can use other logical operators. For example, with the matchbook, species, chromium, the or, which is the colon operator, chromium or manganese, and species 3, and catalog is ICSD. And you will see that you will see a bunch of compounds that contain either chromium or manganese. You see there's chromium everywhere. Let's hope I find some manganese in the first page so you see that I'm not lying to you. Chromium, chromium, chromium. There's manganese, aluminum, cobalt, manganese, some alloy here. It doesn't have chromium, but it has manganese because you're using the or operator. So matchbook here is species, chromium, or manganese, and species is 3 in catalog. So ICSD. You can make these arbitrarily complex, just like what you did in the search page. So let's do the same thing. Let's do end species 3 and catalog. ICSD. And now with this, we will build the species query. So we want chromium and selenium or chromium and tellurium. Chromium and selenium or chromium and tellurium. This is the matchbook. The question, again, the question in the chat, will OR return compounds containing both chromium and manganese as well? Yes, it will, because chromium or manganese is true when both of them are in there. If you want to avoid this, AFLUX unfortunately doesn't have an exclusive OR, the search page does. You will have to build it in a different way. I can write this in the chat real quick, but it is essentially, you will have to do chromium and not manganese, or not chromium and manganese. So this will essentially be your exclusive OR, and the search page will actually convert that exclusive OR into this kind of directive. So this is how you can avoid having both of them at the same time, but a simple OR can have both, yes. So here are the matchbook for this query. And if you run it, you will get 115 compounds, and just scroll back up for the link. Here it is. So you will see that it has chromium and selenium, and there are some that have chromium and tellurium in here. Again, chromium and selenium. There might be some more tellurides in there, but essentially this is how you can make this arbitrarily complex. As long as it is valid syntax with these operators, you can make these species requests or any requests as complex as you like or as you need. Any questions about how to build these species, these operators, these logical requests? So you just need essentially 3 logical operators, and, or, and not. Not is the exclamation point, and is a comma, and or is the colon. So these are very important. Yes, we have a question, Eric.
So in this last list that we did with the 2 sets, the and or with the exclusion, this 115 outputs,
Yes.
that list ends for me at like 64 of 115. Why is it doing that?
This has to do with the paging directive. We will talk a little bit more about this later. But the reason why it does that is because if you do a request in your browser and you search through like all the 3.5 million entries, and your search is so broad that it actually returns millions of entries, your browser is going to crash really hard. And this is avoided by default by using the paging. There are ways to return everything, and we'll talk more about this directive later on.
I mean, is there a way at least to gain access to the other 60 items in this 115 list?
Yes, there is. I will
We'll
talk
get to
more
that.
about the paging directive and how to get access to them. But if you want to do it now, you can use paging 0.
0. Okay. Excellent. Thank you.
And you get everything back. But we will talk more about the number of results in one page and how to get everything later on in the session. Any more questions? Don't see any more questions, so Now that we talked a little bit about the logical operators, I want to introduce another one that is going to be very important for filtering results. Somebody already asked, how do I get just in species without limiting it? And we will do this the following way. So we will just retrieve the band gaps with the EGAP property of all quaternary compounds. So n species shall be 4. We don't use the ICSD catalog, we will just use EGAP and species 4. And it will run a little bit because it's a lot of entries, but we see that we just get EGAP here in the results. The problem here is it all says null. Why does it say null? Because we haven't calculated the band gap for this particular compound. AFLUX doesn't really care if we did. If you say return EGAP, it will just search for EGAP no matter what it is. So what do we do to only get results back that actually have a band gap? For that, we're using the so-called loose operator. The loose operator is the star, and we put that in between the parentheses, EGAP, parentheses, and now when we do search for n species 4, put that in the matchbook here. We see that we now only have entries that are that have a band gap. A lot of them here are 0. So what if you're not interested in metals at all? What if you're interested in semiconductors or insulators? Is there a way we can further limit what we get back? We can use the loose operator for exactly that purpose as well. Let's say we want anything that has a band gap of 1 electron volt and above. The syntax for that is 1 star in species 4. So I get those. So 1 star essentially means that it has to be 1 or greater than 1. This is what this 1 star syntax is. I can show you just to demonstrate. See here, we have band gaps. We go all the way up in the results section. We see we have EGAP 1. You will not find in the results, even if you show all of them, any kind of band gap that is smaller than 1 electron volt. That's a syntax for greater than or equal to 1 electron volt. It's the 1 star. Also put that in the chat. Can we also look for anything that's smaller than equal to? Yes, we can. The syntax would be to star 3 in this case. You want to look at something that has anything less than 3 electron volts. Let's also do n species 4. And we can combine the two to have something like between 1 and 3 by combining the two, 1 star and star 3, and putting the AND operator in between. And when we look for this one, here you see I have paging 0 to return everything. And if you look at the very end, we see we have a band gap of 2.9998 here. Apparently there is none that has exactly 3. And when we scroll all the way up in the results, we see that, that's a lot of results. So we scroll all the way up to the results. Colab is preventing me from opening everything. But if you open this maybe in a browser, I think 3,000 entries is still fine. You will see that the lowest number here will still be 1 electron volt. You will see this particular entry. So let's maybe go ahead and put the matchbook in the chat. Any questions about how to use the lose operator? So the lose operator can be used to say that I want a non-null result, which sometimes you need to do for things like the band gap, for which we don't have for every single entry. And you can use the lose operator also to filter your output. So you can use it to say I want for example, a band gap that is 1 or larger, or 3 or smaller, or you can combine them both with the AND operator. I don't see any raised hands or questions in the chat. So I want to talk fairly quickly because these will probably not be as common. Let's, for example, look for a particular entry with a certain AUID. So AUID, just copy any one of them from your result. And let's look. We get nothing back. Because we get nothing back, even though we know that this entry has to be there. I mean, we just got it back. It has to have a certain AUID. The reason for that is that we have this colon here in the result. AFLUX thinks this is an OR operator. So in order to prevent that, we can use the single quotes to tell AFLUX that everything in between these single quotes is a string and should not be used for any kind of logical operations. And when you repeat that query with the string operator here, you will see that you get the result back. So any time you have like a comma or any kind of AFLUX operator in your search, and you don't want it to be an operator, then just use the query, the string operator. Another thing that can be used, that can be fairly useful if you want to just limit the output and limit the bandwidth, or if you just don't want repetitive data, is to, for example, when we looked at EGAP and species 4, we're looking at that query again. You see that N species is always 4, which is pretty obvious, and we don't need this repeated constantly because we know N species is 4. So if you want to just not have that output in your final result, you can use the $, just the mute operator, in front of that particular property. And when you do the search again, you will see that N species is not in the results. So this is a way for you to filter for a property without having it return and bloat your output unnecessarily. So just put a $sign in front of it. You can also mute these default parameters that you get back. I will show this with, for example, the AUID. Species 4. And if you just do $AUID, you'll see that the AUID is completely gone from the output. Any questions about the matchbook? We will now later go on to the directives. Okay, Cameron.
Yeah, I just had a quick question. My muscle memory keeps putting spaces after the commas I'm typing. Is that a problem when you're reaching out to the API? Or I know some coding systems, commas after spaces doesn't matter. Does it matter here?
Let's figure it out. Yeah, it seems to have a problem with that. Yes, it does. It does not like the spaces.
All right, good to know.
I can confirm that.
Yeah, it doesn't like space. So if you are using it in a Python script, I would just recommend sanitizing that beforehand. Something maybe that we can think about, sanitizing the spaces in between the logical operators, but it's hard to do because it's not a trivial problem to solve, because sometimes the space might be desirable.
Yeah, I was more just wondering whether it was something I should ignore or whether it's something I should scrub myself. That's not a problem on your end. That's a user issue.
Yeah, but easing the use of software is never a bad idea to consider. So, yeah, good question though.
Quick question. Is the sequence of queries in the matchbook, does that matter a lot? Like, should it be the sequence as in like EGAP and species? Can I switch it, make it first and species and then write EGAP? Would that change my output?
It will. I will talk about this in a little bit. It sorts by the first property. So if you put N species first, it will sort by N species instead of EGAP. That's the only. Anything after the second part, anything after the first keyword, doesn't matter in which sequence you put it.
Okay, awesome. Thank you.
Any more questions? I like all the questions because they always kind of foreshadow what I'm going to talk about. That's not the case, then we got questions in the end, or like at the very beginning, sorry, not the end, at the very beginning. Why do I only see 64 results? And that is because of the paging directive. The paging directive shows the results pages. So the default is 64 entries per page. And if we add paging 1 to the directive, we will get the first 64 results. But what about the other ones? If you change paging, for example, to 2 instead of 1, you see we get the next 64 results. Here's 128 at the end. You can change the size of the page, for example, by you can change the size of the page by doing, for example, let's say we want to have the first 100 entries by using, for example, paging 1, 100. The second argument in that list is the size of your page. So when you do this directive, you see you get the first 100 results. And if you change the paging directive to 2 and 100, you see you get the next 200 results. So if you want to just decrease your network traffic or make sure that you are just getting your results back in smaller chunks, then this paging directive can be very useful. And the way how I recommend using that is to have a while loop until you don't get any results back. I can show you what happens when you go past the page limit, let's say page 55, which is not a valid page because you only get 3,000 results back. So when you do paging 55 and 100, you get an empty array, nothing is there. So if you have a while loop that just keeps increasing the page number, then you will get, at some point you will get nothing back, and then you can stop your loop. Another thing that you may notice, or I'll just go back to a valid page, is that you have a, that this is kind of listed as a JSON key. This is very much for human, also the kind of a semi-human readable form. If you want this without these keywords, if you just want a simple array, you can also use the mute. You can use the mute operator. So when we look at paging 1, but with the mute operator in front of it, you see that you don't have these keywords anymore, which I think is very useful, or is much more useful for any kind of high throughput or big data or machine learning analysis. Just have it as an unsorted, as an unkeyed array. So that's an option that you have in paging. And the last thing somebody asked how to get everything back is using paging 0. Well, paging 0, and with that you get everything back. And in that case, again, be careful what you wish for. If you want to get everything, you absolutely can. Is this advisable? That's a good question. If you open a JSON with 3 million entries in your browser is likely going to give up and crash. So be careful with paging 0. It's not as much of an issue when you're using Python or wget, but the result you get back will be fairly large. Any questions about the paging? Doesn't seem to be the case. Paging can do more than just giving the number of results back. It can also sort. By default, when we do paging 1, and when we do paging 1, for example, or any other page number that you like, but paging 1 will show the first results. You will see, and when you look at the results here, you see EGAP is sorted in ascending order. So it's 1, it's 1.0003, 0036, etc. We'll keep going up. How do we do this in ascending order? It's by adding a minus sign in front of the number. So paging -1. Paging -1. And you will see at the very top, when you scroll all the way up to the results, is we have 2.9998, which, if you remember at the end, when I did the paging, the big request of paging 0, that this entry was at the very end. So with -1, you can do that. You can do ascending order. It works for 0 too. So paging -0 is returning you everything and returns it in descending order. Then, as I mentioned earlier, it's always sorted by the first property, and in this case it's EGAP. I can show you real quick how that looks like. Here we see EGAP. It's ordered in descending order, 2.9998. It's the same thing that we had before. And then it looks like I forgot to add the paging directive here. Paging -1 to sort in descending order. Here we have spin atom in the first position. And you will see that the entry that we had before with EGAP is not the first entry anymore. It's the one with the highest spin per atom. here you see it's going down. And unfortunately, right now, AFLUX does not do complex sorting. It doesn't do the first and then the second and then the third. It only sorts by the first property for now. So if you want to sort, just put the property in the first position. Any questions about sorting or the paging directive in general? See any raised hands? The last thing I want to talk about before we go to some exercises is aliases. Imagine the following scenario. You want to look for any compounds in the zinc blend structure, like a metal and a chalcogen, space group 216, and Pearson symbol CF8. That's the zinc blend structure. And now imagine how that query would look like. We want a chalcogen, so we have oxygen or sulfur or selenium or tellurium, and every single metal. This is an absolute monstrosity of a query, and nobody wants to do that. I'll show you anyway how that looks like. See, we get about 350 results back, exactly 350 results back. We can have shorter queries with aliases. So instead of just typing out all these metals and all these chalcogens, you can use the same keyword that we had in the search page. You remember the little panel that has these element groups? We have those in AFLUX too. So you can type chalcogens and metals instead and use that query, and AFLUX will automatically understand what it is and what it means. So you see we also have 350 results back. You can compare with these results to see that they are the same thing. I just wanted to demonstrate these aliases. Here are the ones that we support. They are, if you know your periodic table, they are pretty easily recognizable. They are also listed in this help directive, help aliases. I can look at this here, and here you see exactly what AFLUX replaces these aliases with. They're case sensitive, so that's just something to keep in mind. But yeah, in this help directive with the aliases, you can see what they're being replaced with. Here's the actual, like the original paper here at the end, if you're interested in more of the inner workings of AFLUX. And before we jump to the exercises, are there any general questions about AFLUX, about anything that I was talking about earlier? If that's not the case, I will maybe give you 10 minutes for the exercises. And we'll demonstrate at the end, and I will stay here to answer any questions or fix any problems that might come up. Getting the question, are there any formats other than JSON? Yes, there are. There are two more. There is, for example, HTML, which will return it as a formatted table that's more human readable. And we also have, if you're familiar with the AFLOW out format, AFLOW.out format, we also have some kind of a pipe separated kind of custom output format with AFLOW that you can use. You see that these are more helpful for codes that don't have native JSON capabilities, for example, C++, where you have, for example, not an array, but it's more comma separated instead of having a full-fledged array. So yeah, these are available. JSON is just the most commonly used one, so that's the one that we promote. JSON is also the default. So if you don't put any format in there, you will see it will return JSON. The difference between JSON and including format JSON and not including format JSON is how it looks like in the raw data. In Firefox, it's not a problem because it pretty prints everything automatically. But if you're in Chrome, you'll actually notice the difference. So here, when you look at the raw data, it's pretty printed when you include format JSON explicitly. If you don't, then it will be very compact. So, which could be very helpful to reduce network traffic as well. So. I'll go ahead and start demonstrating the solutions to these exercises. So the first one is the same thing, the same exercise that we did for the search page. That was exercise number 2. From the ISSD catalog, we want to find the VRH bulk moduli for materials containing titanium in the AFLOW database. And then we want to find the material with the highest bulk modulus, get the lattice parameter, the lattice type, not the lattice parameter. Apologies, the space group, and if it's a metal or an insulator. So we need to think about how we want to put this query together. The most important part, or one of the most important part, is we want the material with the highest bulk modulus. So that means we want the AEL bulk modulus VRH parameter to be at the very front. Because recall, the first property is the one that AFLUX sorts by. And we use the lose operator to make sure that we actually get something back that is not null. So now we can get together the rest of it. We want materials in ICSD catalog. So catalog is ICSD, containing titanium. So species has to be titanium. And we want the 2 more parameters, the Brave, lattice, the lax, and we want EGAP type. That is the matchbook that you can put together. Now the directive. Technically, what you need to do is we want the highest bulk modulus, so we want to sort it in ascending order. So paging needs to be -1 and format JSON. That's one way to do this. When you do that, you can scroll all the way up if you like, and you will see we get iridium-3 titanium, or if you want to be, if you don't want all the other stuff, you just want the one with the highest bulk modulus, we can also just reduce the page size to 1. And with that, you only get 1 entry back if you're interested in just the highest bulk modulus. So I'll post these 2 in the chat for the matchbook and the directive. The next one was to determine the bulk moduli of all binary materials in the AFLOW database with a transition metal chalcogen and a band gap between 1 and 3 electron volts. So again, the bulk moduli are supposed to go to the front because this is what we want to sort for. AL bulk modulus VRH. Binary materials, so in species is 2. With a transition metal and a chalcogen. So species is transition metals is where we can use the aliases, chalcogens, and then the band gap between 1 and 3 electron volts. So now the ones with the lowest bulk moduli, we want paging to be 1 because we want to sort in ascending order, and to list only 5, we have the page size to 1. We set the page size to 1, format JSON. So let me put those in the chat as well. And again, you will get all the entire notebook completely filled out. I'll provide that to you over the course of the day. And you see at the AA bulk modules, VRH is some hafnium sulfide, and then a molybdenum selenide, tungsten sulfide. So we have a bunch of metal chalcogenides, which is exactly what we want, transition metal chalcogenides. And the last exercise was to narrow the choice of transition metals down to iron, nickel, cobalt. So, and we want the largest magnetic moment, so spin atom comes first. Species is, in this case, iron or nickel or cobalt. And chalcogens. And what else do we want? We want the bulk modulus, or AL bulk modulus, VRH, has to be not null. Chemical formula space groups are always returned. And we want the ones with the largest magnetic moment. So here again, paging has to be -1, and we want the first 5. So page size is 5. And format is JSON. You see, when we sort this by magnetic compound, by magnetic moment, we see some iron, cobalt oxides, another cobalt oxide, a different space group, something more complicated, cesium iron oxide, and nickel oxide here. And then put those directives and matchbooks in the chat. And that'll be it for the exercises. Any questions about anything I've talked about? Should be the search page or AFLUX. AFLUX, as I said, has a little bit of a learning curve, learning the operators, and what you can see, you can actually put quite complex search queries, and the AFLOW database will return all the results that we have, all the entries that we have to fulfill these conditions. So.